When you start to work with some more complicated integrals, you need some more sophisticated tools to help you do the antiderivatives. In Calc 1, we usually have U substitution at our disposal, and then we also have, tables of integrals that we use for specific formulas. But as things get more complicated, we're going to start to develop some more sophisticated techniques, as I mentioned. So one of those things is called integration by parts, and I like to think of this as the closest thing we have to a product rule in integration. And so I'm going to go ahead and derive that formula for you, and then we'll do a couple examples. It's going to be that simple. So let's get started. When I derive the formula for integration by parts, I like to start with the product rule from derivatives, something that we learned in first semester. And so you'll remember that if you want to take the derivative of a product, and we typically call the two functions in the product u and v. So if we want to take the derivative of uv, our formula looks something like this. It's the first function u times the derivative of the second function, which would be dv over dx. I'm just using Leibniz notation here, and there's a reason for that. And then we add on the second function v times the derivative of u du over dx. When we memorized this thing in class, we did uv prime plus vu prime, or vu prime plus uv prime. But I want to stick with the Leibniz notation because we're going to manipulate this thing and come up with a formula for integration by parts. So the first thing you'll remember is that this notation, dv over dx and du over dx, those can be considered differentials too. So essentially what we're going to do is we're going to multiply this whole thing by dx and get these dx's to sort of cancel out. And when we do that, we get the differential of the product, uv, equals u times the differential of v dv plus v times the differential of u du. And then what we're going to do is we're going to basically do the antiderivative on both sides. So we're going to integrate this sucker. Oops, that is not a great integral symbol. Let's be a little less careless. So I'm going to do an integral on this side, and then I'll do it on this side also. And I'm going to use the sum rule to break this into two pieces. Now, when you integrate a differential, I hope you'll remember that you just get back the function. So if we were integrating dx, it would be x. Since we're integrating d of uv, we get back uv. And then we have no idea what we're going to do with these two integrals. So I'm just going to write them. Oops, that should be a v. So it's the product uv equals the integral u dv plus the integral v du. And then to finish off the derivation of the formula, we're just going to use a little arithmetic to rearrange this thing. If I subtract the integral of v du from both sides, I get this equation. The integral of u times dv equals the product uv minus the integral of v du. And this turns out to be the integration by parts formula. Oh man, I need a bigger highlighter. I just made a weird giggle there. Sorry about that. So this is our integration by parts formula. And the reason I'm calling this somewhat of a product rule is you'll notice in the original integral right here, we have a product, u times the differential dv. And so we are going to be able to use this deconstruction here, this equation, to turn a product u dv into some other expression that hopefully we'll be able to do the antiderivative of. So that's our goal. And I'm going to show you a couple of quick examples where we can use this technique to transform a problem that we can't do into something that we can do. That's the goal. So let's see this thing in action. So our goal here is to find the antiderivative, right? The indefinite integral of square root of x times the natural log of 3x dx. You're not going to find a formula to help you deal with this thing in your formula tables. And that's where this strategy we call integration by parts comes into play. So as you're setting this thing up, you'll notice in the formula we have a u and we have a v and we have a dv and we have a v, right, and a du. We have all these pieces. And what we have to do is we have to, in a strategic way, choose a couple of these and work our way to finding the rest of them. So in terms of our steps, the first thing we always do is we choose u. You get to choose u, right? That's one of my favorite puns. Now you're going to develop some experience as you're doing this, but typically there's a few things that you want to look for. If you had a factor that was just an x, we would probably choose that as the u, because when you take the derivative of x, it turns into a 1. It makes the expression simpler. Another thing that I'll recommend that you do almost always is if there's a natural log factor in your expression, go ahead and choose that for u. And it just takes some experience until you get used to these choices, but you always choose u first. And so since I mentioned that I like to choose the natural log expressions, right off the bat I'm going to choose u to be natural log of 3x. Now, once you make your u choice, everything else is du. So I'm going to choose dv. I'm going to put choose dv as my step, but you're really forced into taking everything else and making it dv. So this square root of x and this dx, those are all dv. And then what you do to get organized in these problems is very similar to u substitution. You're going to write down u equals natural log of 3x, and we're going to take the derivative. And that'll help us solve for du. So the derivative of natural log of 3x, you probably remember, is 3 over 3x, which is just 1 over x. And then when I solve for du, don't solve for dx this time, just solve for du, you get 1 over x dx. And the reason I'm doing that, you'll remember, we need, in our formula, we need a u, and we need a du, right? There's the du right there, and there's the u right there. So I've got those two pieces taken care of. Now, since we chose natural log of 3x for our u, everything else, that should be dv. Everything else in the expression is dv. So the square root of x dx, right, the square root of x dx, that's my dv. This is already a derivative, so what we're going to do is we're going to work backwards and we're going to do the antiderivative to figure out what v is, right? When you do the antiderivative on dv, you get v. And then we have to do the antiderivative of the square root of x dx. Well, the antiderivative of x to the 1/2 is 2/3 x to the 3/2. We'll use our power rule. Don't worry about a plus c right now. That plus c will get taken care of in the formula when we finish this thing off. So now what we have is we have the 4 pieces that we need to finish off an integration by parts. We've got the u and the du, which I already circled in yellow, and now we have the v that we need here. We actually only need 3 pieces. The dv is the thing that we use to get the v. All right, so we have this definite integral, which is written in black, indefinite integral, square root of x natural log of 3x dx. We're going to turn that into this expression here. So that's going to be u v. So that's 2/3 x to the 3/2 times natural log of 3x. That's the u times v, minus the integral of the v, which was 2/3 x to the 3/2, times the du, which is 1 over x dx. And if the universe is cooperating with us, we should be able to do this integral pretty easily. And it turns out we can. I'm going to clean it up a little. There's not much to clean up here. This is still 2/3 x to the 3/2, natural log of 3x. But I can simplify 2/3 x to the 3/2 times 1 over x. That's just 2/3 square root of x. So I'm just going to do I factor out the 2/3 and I clean that up, and now I just have to do the antiderivative of the square root of x, which I already did over when I computed v. So my final expression for this answer, it's not pretty or elegant, but it is correct. So I've got the uv, and then here's the answer for the integral of v du. That's going to be 2/3 times 2/3 x to the 3/2. So that's 4/9 x to the 3/2. And now we can stick the plus c on. That plus c takes care of all the antiderivatives that we did. And I'm just going to highlight this thing with my thicker highlighter pen. And I'm going to give myself a little kudos for doing this thing right, coming up with the answer. I stopped writing my steps because I got all excited about what was next. After you choose the u and the dv, we did the derivative of u. So step 3 was du over dx. Step 4 was to find v using an integral of dv. And then step 5, we filled in the formula. So this is a terrible set of notes here. But that's our strategy. We'll go ahead and we'll try it again on another problem and see if I can make it a little clearer. It turns out integration by parts is a perfect technique for doing the antiderivative of logarithmic functions. So here we're going to do the indefinite integral of log base 2 of x, but this would work on natural log of x or any logarithmic function. So remember, our first step is to choose a u. And I mentioned that if there's a log in the problem, we want to go ahead and choose that for u. So I'm going to choose log base 2 of x as my u for this problem. And that means everything else that's left is my dv. Now, notice the only thing that's left is dx. And that's okay. We'll just write down dv equals dx. So we did step 1, choose u. Step 2, dv is everything else. Step 3 was to find the derivative of u. So du over dx equals, you might have to look this formula up, but I happen to remember that it's just 1 over x log 2. And if I solve for du, which is our part of our step here, we get 1 over x log 2 times dx. So we finished that side. For the dv, when you integrate dv, you get x. So v equals x. So now I have my u, my du, and my v. And I'm ready to fill in the formula. The formula says that this integral, log base 2 of x, is the same as u times v. So that's x log base 2 of x minus the integral of v, which is x, and du, which is 1 over x log 2. 1 over x log 2 dx. Notice the x and the 1 over x are going to cancel. And so this is really just the antiderivative of a constant 1 over log 2, which is simply 1 over log 2 times x. Or I'm going to write it as x over log 2. So my uv is x log base 2 of x minus this integral, which we just said was going to be x over log 2. And then don't forget the plus c. Oops. Now I'm actually going to do one more example for you that's similar to this one. And it'll be a formula that we can just put on our, you may have already seen it on an integral table, but we'll put it in our list of formulas and we'll use it from now on. I'll do it on another screen. I could fit it on here, but why squeeze it in? So the answer for the integral of log base 2 of x is x log base 2 of x minus x over log 2 plus c. A more general integral is just to do the integral of log of x. So we'll do that on the last slide here, and then we'll call this video good. Up until a few minutes ago, finding the antiderivative of the natural log of x was impossible for us, unless you looked it up online, because we didn't have the techniques. But now that we know about integration by parts, we can do something that's seemingly so easy, but really is kind of complicated. So we know the derivative of natural log of x is 1 over x. What we haven't learned yet is what's the antiderivative for natural log of x. So we'll use integration by parts to figure this out. I'll choose u equals natural log of x. That means dv is everything else, so dv is dx. When I do the derivative of natural log of x, I get 1 over x, so that means du is just going to equal 1 over x dx. The antiderivative for dv is just x. And now we can set up the formula. It's going to be u times v, which is x, natural log of x, minus the integral of v, which is x, times du, which is 1 over x dx. And this obviously cleans up to be just, oops, that's not an equal sign. The integral of dx, which we happen to know is x. So whenever somebody asks you, hey, what's the antiderivative of natural log of x, you're going to say x natural log of x minus x plus c, and you'll have it. And this integral here is no longer a mystery to us. We know that it's x log x minus x plus c. Okay, so that's an introduction to integration by parts. We went through the derivation of the formula. We went through 3 examples, and I did a terrible job at making a list of the things that you're supposed to do. But in general, choose your u. dv is everything else. Take the derivative of u to get du. Take the antiderivative of dv to get v, and then put the stuff in the right place. And then remember, the key to this whole thing is that if we break it apart correctly, hopefully we'll be able to do this integral, because we know that we weren't able to do that one. Okay, that's integration by parts. Keep up the good work. Take care.